Hello everyone, welcome. My name is Mayank and today I'll be presenting my assignment for COM 359. And the topic for the assignment is the runtime benchmark comparison for the Python libraries which are used for scientific calculations, which are NumPy and SkipPy. So the main question that we're going to be looking into today's presentation is which one is faster at computing the inverse of 5 by 5 matrices. So as we took both and did some trials on them, you can see we used 10,000 benchmark trials and we used inverse matrices over which 99 more than 99% of matrices were invertible, and we found out that roughly 1.5 times NumPy is faster than the SkipPy. Matters at all. Let me frame the question more clearly for you guys. So for the 5 by 5 matrices with integer entries, does the NumPy or the SkipPy is faster? And why there are differences? We're going to explain it by three key factors. So the first motivator is that the matrix inversion is a very fundamental operation and it's used in very wide scientific computation like physics, simulations, computer graphics, machine learning, and other numerical solving problems. When we are inverting millions of matrices in a very tight loop of time, every microsecond difference per call adds to the real second of runtime. The second part is the NumPy and the SkipPy both are very scientific libraries in Python, and developers choose between them, understanding the performance trade-off not only in theory but in practicality helps them make better choices. And finally, the main motivation is perhaps the most interesting one. The most performing benchmark focus on matrices which are smaller. Specifically, n equals to 5 is very understudied. At this scale, the Python API overhead actually dominates over the underlying layback computation, making it unequivocally revealing about how these libraries are implemented. So let's dive into that. Let's go through the experimental designs that we have. So in total we had 5 designs to implement our whole assignment. So the first thing we did was we generated the matrices. So to generate the matrices, we used the numpy.random function to generate 10,000 matrices, and each matrix have a entry of integers from -10 to +10. After that, we use the float function to convert the integer into floating points, as the LAPAC library is much more compatible with the floating points instead of the integers. The second step we did was the invertibility check. So before timing each of the matrix conversion, we want to check the invertibility of each matrix. So this was basically done by checking the determinant of each matrix using the determinant function from the same library, and if the determinant was smaller than 10 to the power of -10, it was considered as singular matrix, and the threshold for the floating point degeneracy was measured. We timed them individually. So this is, I think, the main part of the experiment. What we did is we used the prep counter, which is the Python's highest resolution timer. We took each call separately instead of taking them in batches, which help us to observe the per call variance. And then after taking the measurement for each of the experiment, we converted those timings into microseconds by multiplying each timing to 10 to the power 6. After that, we did a warm-up discard. This is basically for the first 200 trials we took and discarded them. This is very important because the first few calls are systematically slower in Python due to the bitcode compilation, the CPU warm-ups, and the operating system page faulting. This help us to stabilize all of these effects and help us to give a better statistical approach. After doing all that, we run our code and we took the statistics of the rest of the trials that we had. So in total we had 9800 observation. So we computed the mean, the median, the standard deviation and the percentile with the maxima and the minima. We also counted the successes and the failure of each of the trials. Show you the actual code that we used to implement these functions. So the core function was called time library and it took the list of matrices on an inversion function and a label. So the time looping is deliberately simple. For each matrix, we record the time using the prep counter before the call. Then we execute the inversion and then again we use the prep counter again to record the time afterwards. And after doing the recording of the time, we converted each time into microseconds and put them in a list. Any exception was thrown away if it was not a singular matrix. Keep the stats clean. So after the looping, we basically use the four main implementation. The first one is the prep counter, which is a OS clock monotonic, which is very precise up to nanoseconds. This is the exact kind of clock that we need for this experiment. Then after that we use the warm-ups, which is again we discarded the first 200 trials just in case if there's any slow or rundown of the system. And after doing that, we use the individual wrapping instead of taking the whole batch at once. This is very expensive in terms of time, but it gives us very precise measurements, which is good for the stats. And after that, we use the exception handling using the ling error function on the singular matrix. This function caught any matrix which was not singular and just remove it from the start. That keeps the statistical validity of our assignment. About the complexities of our algorithms. So first we have the time complexity, which is cubic in this case. This is cubic because we perform a LU factorization on that, which is basically multiplying three different matrices at a time. So we have the P matrix, which is the permutation of the matrix, the L, which is a lower triangular matrix, and U, which is an upper triangular matrix. And this whole thing cost us 2/3 of our complexity time. And after that, we have 5 by 5 matrices which have about 83 floating points in operation. That this altogether takes a lot of time to compute our matrices. After that, we have the space complexity, which is quadratic. This is just an output matrix for n equals to 5. That's 25 floats value, exactly 200 bits. It's not too much, but it still takes a little bit time. Here's the critical point. Both library ultimately calls the same LAPAC library for the LU factorization. The mathematical work performed is bit for bit identical. There is no difference between NumPy and SkipPy calls. This means 1.5 times the speed up we cannot observe by explaining the algorithm differences. This must come from the Python layer from LAPAC above wrapping the code. That's exactly what we'll explore in the next slide. Libraries call the same LAPAC routines. Why the NumPy is almost 1 time faster than the SkipPy? The answer is entirely based on the Python API layers. So when we look at these two stacks of NumPy and SkipPy, NumPy calls the function directly called underscore unmath underscore, which is directly called from LAPAC and it's a thin wrap with minimal overheads. But in the case of SkipPy, the SkipPy first checks off a few things. It checks for the finite equals to true is the default setting for that, and before calling the layback, SkipPy function scans every element of the matrix. This takes a lot of time because for the 5 by 5 matrix we have 25 element checks. So the complexity gets to n squared automatically. At first glance, 25 checks sounds irrelevant and trivial as well. But remember that the LAPAC computation for n equals to 5 is about 83 floating point operation. So the check finite scan is very large and it roughly takes 30% of the total computation time. This is where the 1.3 microsecond overhead comes from the NumPy. Now let's look at the empirical results that we got by running 10,000 trials. And we remember that we discarded our first 200 warm-ups and then we did the stats on the rest 9,800 observations. As you can see on the top, the 5 headline numbers that we get were NumPy mean time was 2.31 microseconds, where the SkipPy mean time was 3.63 seconds microseconds, and the speed up was 1.5 times of the SkipPy. The NumPy median was 2.29 microseconds, whereas the median for the SkipPy was 3.54 microseconds. As you can see, you can look for the full result table down here. This follows a very important pattern. First, the mean and the median are very close for both libraries, as they being 2.31 for NumPy and 2.29 for SkipPy. This tells us both of the distributions are fairly symmetric with low skewness, which validates the mean as a reliable central tendency for the measurement. For some of the resulting figures that we got out of this experiment. So the figure 1 is a bar chart showing the selected percentile value for both libraries, as you can see, acting as an approximation for box plot produce the actual figure files here. And the second figure that we have here is a histogram. This shows the density of the runtime represented here as smooth line charts. The original figure file underscores the histogram, shows the full density histogram with 54 bin trimmed in 99th percentile. As you can look at the figures, the NumPy is slightly better than the SkipPy. For our next figure, we have a CDF cumulative runtime. So for this is particularly useful way to make and read data because you can directly ask questions like what fraction of NumPy call finishes within 2.5 microseconds. You can get the exact and precise second codes at for each libraries to see what library was good at what time. Wondering, we took 10,000 matrices, out of which how much were invertible and how much were not usable at all. So as you can see here, we took 10,000 matrices and out of which 9,998 matrices were invertible, only being 2 of them as a singular matrix which we discarded in our experiment. So this gives the conversion rate over 99% in this case, which is really great for our results and the practical implications of this project. I want to be clear about the hardware and the software environment that I use for this experiment. Because the benchmark results are always platform specific and you get different results based on different kind of platforms and software that you are using. The measurement that I presented was taken on my Mac using an OS 15.0.1 with an Apple Silicon chip. This is specific M series chip, and the software version that I used was Python 3.13.3 and the NIM was 2.4, and for the skip it was 1.17. So the result would change depending on the type of processor and the type of hardware that you're going to perform the experiment on. And to summarize everything, we got basically four takeaway points from this assignment. The first one that we get is the NumPy is almost 1.5x faster than the SkipPy, specifically for the 5 by 5 matrices. As you can see, the mean time gap was 2.31 microseconds versus 3.36 microseconds in running these programs on each of these libraries. Secondly, we could say that the gap is basically because of the API overhead, not the actual algorithm itself. And thirdly, the gap shrinks and vanishes for the large n. So as we take n greater than 200, which is like if we take larger matrices which have more than 100 entries in a row at a time, then the gap shrinks because then the API overhead doesn't really bother us. And finally, the 5 by 5 matrices that we generated, all of them were almost invertible by being the invertibility rate more than 99.8% in our case. I think this is basically it, and these are the references if you want to look at any of the references that I took my resources from. And yeah, I provided the links here, and if you want to go check it out, uh, for sure. And that's pretty much it, and thank you for listening to the presentation, and if you have any questions, please do let me know in the discussion board. Thank you guys.